So I've shown you several examples of passive transport. All these channels, what they have in common is that we have an external factor regulating them, whether they are open or closed. But once they are open, it's purely a hole, and that hole will let through ions. You can calculate how advantageous that is, meaning the free energy difference, with the usual formula, that delta G equals RT ln, and then the relative probability, for instance, between the inside and the outside. And the easiest relative probability here is just concentrations, for instance, of a small molecule. Or in case of an ion, that's a charge. Well, that we would have the charge multiplied by Faraday's constant multiplied by the electric field, if you remember your physics. And as interesting that is, let's look at something more complicated, that active transport. If we want to go against a gradient where delta G would be positive, then we're going to need something slightly more advanced. Remember this plot. In a cell at equilibrium, we would have excess potassium on the inside, excess sodium on the outside. Once we have that excess, we can open a potassium channel to let the potassium ions flow out, or we can open a sodium channel to let the sodium ions flow in, but they will only equalize the distribution. Something has to maintain that distribution and keep moving atoms in the wrong direction, to take the sodium ions and move them to the outside and the potassium ions and move them to the inside. The component responsible for this is the sodium-potassium ATPase. So it's an enzyme, it's an ACE, something doing something, and it's ATP, it involves ATP, sodium, and potassium. That's a fairly long name, sodium-potassium ATPase, so we occasionally just abbreviate that NKA, which is NKA, sodium-potassium ATPase. The ATP molecule is going to be the one delivering energy here. ATP has lower energy than ADP. If I release a phosphate here, I can gain some energy from that. So let's see schematically how this pump will work. And now we're going to be talking about a real micro machine, which is pretty cool. Let me draw 4 cycles here. Sorry, a cycle with 4. Here's a membrane. It's a membrane. Let's start up here. Let's assume that I have some sort of machinery that is open to the inside of my cell. And when I'm open to the inside of the cell, what will happen is that I will bind ATP. And when I am binding ATP, I also bind 3Na. How should I draw that? Na. While I'm binding those NAs, at the same time, I am releasing 2 potassium ions. So that's a process that's kind of happening in one go. Binding ATP, and as a consequence, I release 2 potassiums and I bind 3 sodiums. What then happens is that this ATP lets 1 phosphate group remain with that protein. And that's going to be, when the phosphate is released, we just have the phosphate and then we have ADP going away. When that happens, this entire molecule will move to a different state. Why? Well, that has to do with free energy. So somehow, when this process happens, there must be a free energy barrier, but once we actually have released that phosphate, it should be better for the molecule to be in another state, this state in particular. When we are in this state, what happens is that we have something that's open to the outside, but I still have my 3 Na bound Na, and there is no potassium. Let's draw an arrow there. Next, we're going to go here. Now I'm still open to the outside, but when I am open to the outside here, what's going to happen is that I will release my 3Na, and I will bind 2 potassiums. In this case, that's in the outside. This is going to be a better state for the channel to be in because this was unstable. What now happens is that at this point the phosphor escapes. When that phosphate has escaped, we're going to go back to my original conformation. And now I'm open to the inside again, and I have 2 potassiums bound, and there is nothing bound to it. Once I am there, I can bind a new ATP molecule. When I bind that ATP molecule, my 2 potassium ions will be released, and 3 new sodium ions will be bound. And then I keep going with the machinery. So in every turn here, I consume 1 ATP molecule and turn that into ADP and a separate phosphate. That expends energy. I use that energy to move 3 sodiums to the outside and 2 potassiums to the inside. So the net difference in electrostatic charge is actually just 1 plus 1 charge that I moved net to the outside, which makes it somewhat cheaper. But I create a fairly large transport of sodium ions to the outside and potassium ions to the inside. And that is what keeps charging this battery. As I hinted at the beginning of the class, this is one of the most important processes in our bodies. Something like 20% of the energy that our cells use is used for this simple cycle. We consume roughly 60 to 80 kilos of ATP per day, or rather we turn over because that it doesn't end up being completely destroyed. It turns into ADP, and then other processes in the cell will of course take that ADP and use chemical energy to convert it back to an ATP. But it's an exceptionally important process that is the basis for the entire energy consumption in the nervous system. This is 2/3 of the energy used in neurons. So the sodium-potassium ATPase has a bit of a special connection, even though I'm not working that much on them myself anymore. The structure was first determined by Jens Skou in Aarhus, and he got the Nobel Prize for this in 1997. Do you see how it's a much more complicated structure, and compared to the ion channels? That's partly because it has to go through all these complicated different states, binding and releasing multiple ions and ATP, which requires a lot of protein. I also have to confess that I lied to you on the previous slide. There are not 4 states. There are at least 8 significant states and a few additional substates. And Paul Nissen, who's a close friend and still active in Aarhus, they've been able to determine structure for quite a few of these states, and by either interpolating them or combining with simulations that Magnus Andersson used to do in my team. He's now a professor in Umeå in the north of Sweden. They've literally been able to determine this process, understand why it's moving between states, and also how this is stabilized. There are a number of relatively severe diseases related to this protein, and understanding the molecular mechanisms of the transport is helping us to design better drugs to treat them. Keep up the good work, both Paul and Magnus.